All right, everybody. How's it going? Not so great? Why is it not going so great? Simon 2, a little harder, a little more fun. A little bit of diversity in solution paths. Cool. Well, maybe this lecture will help out a little bit in a few parts where I won't tell you. Okay, so let's get started. Last class, we talked a lot about, the focus of last class was distributing work onto all of our processors so that we could keep everybody busy. And we tried to do it with the lowest amount of overhead possible. We talked a little bit, like in the last half of the lecture, about how more sophisticated implementations might not even use a shared pool of work, a shared work queue, and you can implement work stealing using a bunch of different work queues to alleviate contention. Today we're going to talk about the other side of optimization, which is trying to reduce the overheads of communication, synchronization, the part that's really hard whenever you try and parallelize a program. So, so today's going to be about explicit or about communication costs. And so this will be a really good time to actually bring back up message passing, which we never really got a chance to talk about a couple lectures ago. Because when we're passing messages between each other, we're really, it's pretty obvious that we're communicating. And so that might be a good place to start today. So we talked about, many times we've talked about this simple grid solver example. And just to refresh your memory, it was while not done. For all the red cells, perform a stencil operation, this blur, and then use the updated results. And then for all the black cells, do the same thing. Basically, every iteration of the solver was two big data parallel loops. Right? Okay. So I would like to say, let's say we want to implement this piece of code on a machine that supports message passing. And for example, imagine you wanted to make yourself a little cluster in the Gates lab, where your cluster, your parallel computer, was one machine talking over Ethernet to another machine. That's something all of you can do. You can go after class, sit down, and make yourself a little mini cluster. But it's absolutely true now that every one of these machines has its own address space. You can't be running code over here that says load address foo, where foo happens to be an address over here. That's just that load instruction. The hardware is not going to support you to do that. But you can send messages back and forth between these computers. We send messages all the time. And so this might be a reasonable way to think about the parallel computer that we're going to use when doing when thinking about this problem in a message passing kind of way. Okay, so yeah. So first of all, up until now, remember I had a single address space. So I had one big 2D array allocation, and every thread or every processor just sort of worked in a different part of the array. But now I have two completely different address spaces. The processors don't share an address space. So I'm going to represent my grid as four different allocations, or sorry, I moved to a 4-node cluster now. And I'm going to represent my grid as four different allocations on each of these machines. So this is a block decomposition of the full grid. And notice now that every thread or every processor on all of these different machines has a different part of the array. It's very, very clear who owns what part of the array at this point. And so let's say that thread 2, let's say all the threads just computed. We've just finished the update the red cell step. And now we want to move on to the black cells. So you know that thread 2, if it's going to compute or update its top row of cells, what information does it need that it doesn't have at this point? What information does it need? Or let me just make it more general. In order for thread 2 to update all of its cells, what information does it need?
It needs cells from thread 1, the bottom row, and then the top row from thread 3.
It needs the bottom row from thread 1, and it needs the top row from thread 3. So if we were just talking about threads on a single machine sharing an address space, how would thread 2 access that data?
Just access
It would just access the data. It would issue the loads and the stores to the appropriate addresses. But now every one of these threads is working on its own machine in its own address space, and so we're going to send messages to communicate the necessary information in the program. So we're going to, thread 1 is going to send a row of values to thread 2 that thread 2 will receive, and thread 3 will also send a row of values to thread 2, which it will receive. And notice that I've modified my diagram because now thread 2 needs to allocate storage in its own address space to store those rows, and those are the cells that I'm coloring here in white. So you'll often hear a term of now it's really clear in this program what thread or what processor owns what part of the array. And so this is a copy of this data. And so you'll often hear, especially in scientific computing, you'll hear people refer to these copies as sort of ghost cells, because there's sort of an image of what the owner's copy of the actual data. And it's been moved here so it can be read by thread 2 in order for thread 2 to update the values that it owns. Okay? And so this is some pseudocode of what this might look like, the logic on thread 2. The thread 2 is going to allocate n plus 2, because that's the width of every row, times rows per thread plus 2. So I made a little bit bigger allocation than I was responsible for. And then thread 2 received a whole row of data into row 0, and that's the one from thread 1. And it received a whole row of data from thread ID 3 as well. Yes, Isha?
Sorry, why is it n plus 2?
Sorry, yeah. It's just to make the code simpler, if you recall, on the actual thing. As we said, it's an n plus 2 by n plus 2 grid. That's all. Yeah, sorry. Otherwise, you need some boundary conditions in the code. Yeah, sorry, that's a little bit janky. Okay, so let's walk through the full implementation of this code, and I'm just going to talk you through it. This is the logic that every thread is executing, every step in this process. So if you look at the start, the most important thing on the screen is the stuff that I've highlighted in red, which are the message sends and receives. So you'll see while not done, if the thread ID is not 0, if it's not the top guy, send something to the guy above you, to the processor above you. Send your top row to the processor above you. And the small guard there is just an edge case on thread 0. Okay? And if we're not the last thread, if we're not the bottom, we need to send our bottom row to the processor that has the rows below us. And then we're going to turn around and issue some matching receives. So we're going to send, and then we say, well, we're expecting somebody to send us data as well, and then we want to receive that data. And then all of this is kind of just normal, right? As I now have all the data that I need. I perform the loop over all the elements. Notice that this is completely sequential within this thread, but of course this is being done by all the workers. And then we keep going on this. When we get down to the bottom of the loop, let's think about what's going on here. So remember, this program is going to be while not converged, keep iterating. So this stuff at the bottom is to try and determine if we were converged. So notice that the code here is computing that local mydiff, the local change in each of the threads. And what's going on in this part of the code, you think? So if the thread ID is not thread 0, we're going to send our local diff to thread 0. And then we were going to receive a Boolean back which says done. So everybody but thread 0 is doing that. And thread 0 is saying, hey, I'm going to receive a message from every other thread, which is the local diff. It's going to add them all up, check to see if convergence has occurred, and then send the results of that predicate back to all other threads. Yes?
Is sending asynchronous, or is it
It's a good question. Let's assume that's completely synchronous for now. Completely synchronous for now. So does everybody kind of see how this works? We've implemented this global reduction by sending some messages. Everybody computes a partial reduction. Every thread sends their partial result to a single thread that's responsible for combining the results. That thread computes the overall change, determines if convergence has occurred, and then lets everybody else know. So the rough structure of this makes sense. I mean, the code's a little bit verbose, but unfortunately, message passing code often does tend to get a little verbose. But this makes sense to everybody, right? Okay. So I want you to take note of what's happened here. All of our computation is kind of done as normal, but notice that the array indexing, all these indices here are local array indices. These are not indices into this big global array like it used to be. Communication is not done via loads and stores. It's now being done by these explicit large messages of entire rows. Synchronization was also done via messages, sends and receives. And that to make synchronization a little bit easier, if you used any modern message passing library, they'd probably give you, they wouldn't just give you send and receive. There's a bunch of syntactic sugar to do many common operations that are implemented under the hood with sends and receives. Like, so we implemented just then a reduce, an add reduction. And you can imagine it might give you some nice simple primitives to do things like go ahead and do an add reduction, or go ahead and send the same message to every single other processor in the system, a broadcast. So I'm glad you asked about synchronous send and receive, because this example that I gave you, I think so far probably everybody has thought about it as, look, I'm going to send a message, and when the message is sent, I'll proceed on. And that's what the question was about, was are sends and receives synchronous or asynchronous? So last time we had a good example of synchronous versus asynchronous, right? A normal function call in C is a synchronous function call. The calling thread moves into that function, and the call does not return until the function has completed. Whereas a silk spawn is an asynchronous function call. It says potentially start running this function, and the calling thread can continue running while that operation is going on. And we can do the same thing with messages. So a synchronous send says, send this message to a student, and when we know that the message has been received, return to the sender. And so that's exactly what I'm illustrating here. The thread calls send of some buffer foo. The data is copied into the network. It's sent over the network. The receiver receives it. The receiver brings it into its own address space so it can start working with it. The sender gets an acknowledgement, and thus the call to send receives. So here's an interesting question. And the reason why I told you that let's think about that previous code in terms of blocking sends and receives is that nobody pointed it out to me. Actually, most years it doesn't occur. Is that the code that we just talked through is completely broken. Completely broken. So let me go back to that for a second, to bring that code up. This was the code. And imagine that. So does anybody see how it's broken yet? Okay, so some people see how it's broken. I'm going to make it very clear why it's broken to everybody here. So we can very easily act out this message passing code, right? So what you're going to do is we're going to do this all in sync, and every row is like a processor, right? And so this code says you're going to all send to the row above you. So you're going to turn around and say hi to the person behind you. Or no, let's say in front of you, I guess. Lower numbers are down here. Lower thread IDs are here. So the first thing you're going to do is you're going to lean forward and you're going to say hi to your friend in front of you. And you're not going to do anything else until your friend acknowledges the fact that you said hi. Right? Okay? So I would like everybody to do that, because after they acknowledge you, I want you to turn around and say hi to the person behind you. And then when they acknowledge, because everybody's friendly in here, then I want you to start acknowledging your friends. So let's do that. So everybody lean forward and say hi. And you're free to continue when you get an acknowledgement. No, you guys. The compiler is broken. Okay, so at this point, can somebody tell me why I'm saying that this code has a big mistake in it? Let me go somewhere else, because it should be very, yeah. So every processor's leaning forward saying, here you go. But I'm stuck until somebody receives this message. But everybody's leaning forward to send. And there's nobody posting to receive. Good. So here's a question. Does anybody have a fix by using only blocking sends and receives? I know we're not going to go asynchronous with this. Let me, yeah.
We could try having all the odd threads send and all the even threads receive or something like that.
Okay, so I like that idea. Let's be a little bit more specific. I mean, you're definitely going off in the right direction. How are you going to do it?
So thread ID modulo 2. So if thread ID modulo 2 is 0, send. If it's 1, receive.
Okay. So which direction? So we have to do two sends though. Which one? So you're completely right, but it's actually a little trickier than it seems. Yeah. So there's 4 operations that everybody needs to do, right? I need to send, receive, receive.
So I guess we're looking at there would be the outer 2 first and the inner 2.
Ah, okay. Okay. So if it was just if the answer, like if you just went with the answer, if I'm an odd numbered row, an odd number processor, I'm going to send. There's going to be some problems actually. And can anybody see what might happen? You won't deadlock actually. Can you think through it? It's actually a little subtle. Maybe we should think through it offline. In fact, the code will work. Yeah. Yeah. You'll be correct, but it'll be completely sequential. Because only you're going to get the guy on the end, he'll send back, and then only then will the next row receive, and then it'll cascade all the way through, so it'll sequentialize the whole thing. Your solution, however, is correct. So the way you need to set this up with blocking sends and receives might be something just kind of like this, is if I'm an even-numbered processor, I send down and then receive from down. And so everybody needs to get paired up kind of in this way. So yeah, that was very good. I think that might be the only time anybody's actually gotten this one entirely correct in 4 years. So very nice. Yep. So I'll let everybody kind of puzzle over this, on your own copious spare time. Okay, so we can also move to a non-blocking send and receive, an asynchronous send and receive, where if I send a message, I'm going to go off and do other things that may happen concurrently or simultaneously with that message being communicated. So in an asynchronous send, the sender is going to say, here, I want to send this message. Start sending this message. The call immediately returns. At some point in the future, that message is sent to the receiver. The caller can be processing, doing whatever he or she wants. They can be twiddling their thumbs. And at some point in the future, the caller can check. Like the send returns a handle. And I can check to see, hey, is the message send associated with this handle H1? Has it completed? And so there is concurrency now between the calling thread as well as the message send. Equivalently, on the receiving side, an asynchronous receive is a promise or a statement that I'm interested in receiving a message. Receive returns immediately, and the caller can check later on whether or not the message has actually been received. Okay. So this is the asynchronous send and receive is the communication analog to the asynchronous function call that we talked about last time in Silk. And in fact, actually, a number of people have asked me about this in office hours. When you launch a kernel in CUDA, like from the host side, when you say kernel launch, that is actually an asynchronous launch. It says start running this kernel, and the calling thread can proceed on, which is why in some cases you see a CUDA thread synchronize after that call just to basically force that call to be essentially synchronous just for simplicity. In most of the cases in the starter code, you can actually remove that CUDA thread synchronize and everything is just fine. But we put it in there just to kind of keep things obviously synchronous. Okay, so is there any questions about message passing? I mean, message passing is not a particularly radical concept at all. We do it all the time in computer science. You're used to, like sending messages to a web server, getting a message back from a web server, and so on and so on. There's one interesting thing that you might want to keep in mind here, though, is imagine that this thread calls send, passes send the buffer foo that it wants to send over to his friend. The call immediately returns, and then maybe the caller thread's like, okay, great, I'm glad I sent that. I'm going to delete the buffer foo. I'm going to free it. Would this be okay? Or would this not be okay?
Depends who has responsibility.
You can define whoever you want. Well, let's say I have responsibility, because the statement of the problem is I want to free it, right? So I have responsibility for cleaning up foo. So I call send foo. It's an asynchronous send. That means that the message will be sent at some point in the future. And then boom, I kill my buffer. I completely delete it. Oh, let me go here. Yeah.
So it depends on whether or not copying into the network buffer is synchronous.
Right.
So like if it copies it right away before send returns, then
Well,
it's fine.
this is the sequence of events that you're promised.
In that case, you could end up like sending whatever's in memory.
Yeah, I mean, you could end up freeing the buffer that the message passing system is responsible for sending, or writing over it or something like that, so you very well could send garbage. Can this happen on a synchronous send? Yes? No? On a synchronous send, can this occur? People are shaking their head no. Why is that? Yeah? No, go ahead. Because by the very definition of a synchronous send, the operation is complete, the message is gone, it's been sent and received by the time call returns to the caller. Exactly. Okay, so any other questions about this? Or should we move on to the next topic of the day? So the next topic of the day is Pittsburgh. And if anybody can find me this bumper sticker, I would be very, very, I'll give you a point of extra credit on something. So Pittsburgh is, believe it or not, like the hot place right now. Many of you have probably seen some articles in the New York Times on what to do when you want to go visit Pittsburgh these days. There's a great article in Politico about how awesome Pittsburgh is. Pittsburgh is the hot place for people of roughly your age. Hopefully you should stick around and do your startups here. Pittsburgh is a pretty hot place. It is the place to be. What's also hot these days is rent in New York and San Francisco. Right? So this is a posting from not too long ago of the median two-bedroom price in San Francisco now exceeding $5,000 a month. So keep that in mind when you are negotiating your job offers in the future. Right? So there's a lot of folks that are going, wait a minute, like Pittsburgh's got it going on. I don't want to be paying $5,000 a month for rent. There's a lot of people moving to Pittsburgh. Maybe we should be doing that too. Right? So all these techies in Manhattan and the Bay Area, they've had a success or whatever, but they're like, screw this Bay Area crap, I'm coming to Pittsburgh. So everybody wants to be coming to Pittsburgh, and let's say we're going to drive this from San Francisco to Pittsburgh, and let's say that we are a safe driver, and we're going to drive at, let's say, 100 kilometers per hour. And I Googled it, and more or less, San Francisco to Pittsburgh on U.S. highways is about 4,000 kilometers. So if I asked you, what is the latency if the operation is, I want to move to Pittsburgh, and I get in my vehicle, and I drive 100 kilometers per hour, and I drive to Pittsburgh, what is the latency of this operation? 40 hours. You just kind of, you get your Red Bull, and you just make it happen, right? Good. So the latency of this operation is 40 hours. Good. Now let's say that, like I said, Pittsburgh's this happening place. A lot of people want to come to Pittsburgh. And let's say that people are driving to Pittsburgh and everybody on the highway is going San Francisco to Pittsburgh, San Francisco to Pittsburgh, and that they're still driving at 100 kilometers per hour. But let's just say, for safety's sake, they're spacing themselves out on the highway by 1 kilometer. You're driving for 40 hours, you need to be careful. So what would you say is the throughput of people arriving in Pittsburgh? Yeah. 100 per hour. And how did you compute that? Exactly, the number of cars passing one spot on the highway in an hour, and let's just say that happens to be the Welcome to Pittsburgh sign. We have, every cars are spaced out by 1 kilometer. They're moving at 100 kilometers an hour. I'm going to get 100 cars crossing this point. So I have a throughput of 100 San Francisco programmers ending up in Pittsburgh per hour. Exactly. Throughput, 100 people per hour. Good. So what would it be? What if it's the case like there's another article published about Pittsburgh, about how Pittsburgh is like really happening, and more people want to come to Pittsburgh. We want to increase the throughput of getting to Pittsburgh. What are some ways that how could we increase throughput?
Wider highways.
Okay, so why would a wider highway help?
Put 2 cars right next to each other.
So let's say we made a 2-lane highway, and we kept the rules of the road the same. What would my new throughput be? 200 people per hour coming to Pittsburgh. This is fantastic. Now, how did you change the latency of getting to Pittsburgh by your solution? So the latency didn't change. The latency remains 40 hours, the time between leaving San Francisco and getting to Pittsburgh. Are there any other ways to increase the throughput of the highway? Yeah, back in the blue.
Increase the velocity and decrease the car spacing.
So one answer would be, yeah, we could actually say, you know what, we're not going to build more highways. That's not practical, but I am driving a Lamborghini. So maybe I can go to something like 150 kilometers per hour, which is still not that big of a deal for a Lamborghini. But now I can, now I'm 150 people per hour. And then you gave another solution, which was?
Decrease the car spacing.
Yeah, I mean, there are many ways to decrease safety on the highways, and we could decide to start packing the highway a little bit more densely. And again, yeah, we could then, let's say if we made it the spacing 500 meters, how would that change throughput? It would double throughput now, because now I would be getting 200 cars per hour through the Welcome to Pittsburgh sign. Good, okay. So that's our little review of latency versus throughput, right? So latency, the amount of time to complete an operation, the amount of time to load data from memory, the amount of time to complete an instruction. When you ping Amazon, you get a latency of 20 milliseconds. If you ask a question on Piazza, it might take 10 minutes for one of my TAs to respond. Bandwidth is a rate, the rate at which operations are performed. Instructions per second, bytes per second, and so on and so on. Okay? So what if there's so many people coming to Pittsburgh, the cops say, you know what? Only one Lamborghini on the highway at a time. Okay, so the latency is still 40 hours. Nothing's changed. But what's the throughput of this system? 1 every 40 hours. It's terrible throughput. In fact, the throughput is 1 over the latency, right? So by actually having multiple cars on the highway at once, we were able to use these resources, the highway resource, even better. And we're going to come back to that in just a second, because I want to talk about pipelining. So a number of people have asked me in office hours, when a core, let's say, issues a load instruction, can it not issue any more load instructions at all until that comes back? Right? And that would kind of be a bad idea, because the whole point of multi-threading is that we're going to have a bunch of stuff going on at once, right? So a really good way to think about pipelining is we're going to move away from our Lamborghinis, and we're going to go into the basement of Morewood, and we're going to think about doing our laundry. So I have 3 resources at my disposal when I'm doing my laundry, or I have 3 things I need to do, right? I need to wash my clothes. Let's say it takes 45 minutes. I have to dry my clothes, which takes 60 minutes. And I've always wondered why these 2 numbers are different, because as you will see in a second, this is quite inefficient. And then let's say maybe you have to fold your clothes. And let's say that takes 15 seconds, right? Or 15 minutes, right? So what's the latency of completing a load of laundry? 2 hours, right, 2 hours. I have to, this single operation is broken into 3 steps. The sum of those steps is 2 hours. Now, it's the case, nobody ever does a single load of laundry, right? You wait until you basically run out of underwear, and you have a lot of laundry to do, right? So when you want to do laundry, you actually probably care a lot about throughput. If you're a college student, you may care about throughput. And so what's one way we can increase throughput? Well, we can go ahead and buy an extra washer, an extra dryer, and we can go ask our friend. And now all of a sudden I have a throughput of what? Twice. So I can now do 2 loads of laundry in 2 hours, which is 1 load of laundry per hour. I've doubled my throughput. What is the latency on the system? Still 2 hours. So it's kind of hard to, go buy another washer, and nobody wants to fold your laundry. So is there any way that I can increase throughput without going off and go buying a bunch of resources? Imagine you did have to do 2 loads of laundry, and there was only 1 washer and 1 dryer available. Yeah.
Start the next load washing while the dryer's on.
Exactly. Nobody waits until you wash your laundry, then you dry your laundry, then you fold it, then you go back and put the other thing in. That would be ridiculous, right? So what we do is, oh, sorry, I jumped ahead, is it's certainly clear that as soon as the washer is done and the wash has been moved into the dryer, then I can get my next load of wash working into the washer. Make sense? Everybody does this all the time. Shouldn't be very... And of course, we can continue this process, because remember, you really built up the laundry. And what is the throughput of this system? Yeah. So I'm achieved this 1 load per hour, which was the same throughput as I had if I was bought 2 washers and 2 dryers. But I'm doing it with just 1 washer and 1 dryer. And what was the key insight that I used in making this scheduling decision?
That the washer can be used again while the dryer is in use.
Because I have this big operation, but really it's broken into some smaller steps, and each of those steps has a different unit, and those units can be working in parallel on different pieces of data, so to speak, coming through the system, right? So now I have a system that has throughput of 1 load per hour. What's its latency? Still 2. Nothing has changed in latency. That's exactly right. So a lot of the times when we say, we can now take this to a little bit more practical, or it's not practical, laundry's pretty darn practical, but a little bit more computer science-y an example, is that when I say that there's a processor can do 1 instruction per clock, really what I'm saying is that the throughput of the processor is 1 instruction per clock, because these instructions might have a much longer latency. And if you take a basic computer architecture class, perhaps something you'll do on the first or second day of class is talk about sort of a very, very simple pipeline where you can think about executing an instruction as a 4-step process. Reading the instruction from memory, that's the orange box. So these correspond kind of to the units in my diagrams from lecture 2. Kind of decoding the instruction, figuring out what you're supposed to do, as well as reading the input operands from the register file, doing the actual work, and then writing the results back. So even though any one instruction takes 4 cycles in this diagram, notice that my throughput is 1 instruction per clock. Now there's something about the program that's necessary for me to be able to do this. Does anybody see what that might be? Yeah. Yeah, the instructions, all the instructions don't need to be independent, but I certainly can't start the next instruction immediately on the next cycle if it depends on the previous one, yes. So there needs to be some amount of independence of some of the instructions, the instruction stream to do this. Of course, if you take a real computer architecture class, you'll learn about a bunch of techniques to kind of minimize the effects of those dependencies, such as forwarding and other things in the pipeline. Did I see a hand? Yeah.
There must be 4 different cores, I guess.
Well, this is just how executing instructions in a single core. But there is an assumption here that inside of that core, there are separate and simultaneously executing units that take responsibility for fetch, decode, execute, and write back to the register file.
4 operations that happen. I guess there must be 4 units that work independently from each other.
Yeah, well, I wouldn't say independently, but they can run simultaneously on different instructions. And in fact, actually, if you looked at the diagrams from lecture 2, I have a different box for IF, execute. I happen to have 1 box for the decode and write back, because that's the context. But yeah, exactly. And this is actually the key to how you can make clock frequency go higher, or was previously, is that by breaking expensive instructions down into small pieces, you can make your clock tick is proportional to how much time it takes to do a small piece of an instruction, not the entire instruction. And so if you look at like a modern, like something in your laptop these days, the pipeline length, the number of steps is very instruction dependent, and in general these days it's about 15 to 20 cycles. And just to give you one more example, breaking an instruction into a bunch of small parts is very similar to the idea that you guys gave me of bringing the cars closer together on the road. Whereas you can think about a piece of the highway as a unit doing part of the process of driving from San Francisco to Pittsburgh. And by breaking this process up into a bunch of small steps, we can really pack the cars closer together. We can essentially overlap their execution of driving time or pipeline its execution. And that's how we were able to get much higher throughput. Okay. So why am I talking about any of this in a communications or in a communication cost lecture? Is we can think about the same thing when we're sending a message. So imagine I'm sending a message, going back to our original example, and I send it, let's say with a blocking send. I send the message, and it might take some amount of time. So imagine that our message is B bits in size. No, sorry, N bits in size. N bits in size, and I have a channel that can transfer at a bandwidth of N bits per second. No, B bits per second, sorry. B bits per second. So the amount of time it takes for that message to get to the receiver is the amount of time, the latency of sending that first bit, for the first bit to arrive, followed by the amount of time it takes to get the whole message through. And I don't have a diagram for this, but you could think about it as, imagine we had a train of cars, a long chain of cars. If I asked you what was the latency of the entire chain of cars getting to Pittsburgh, it would be the amount of time, the 40-hour latency for the first car to arrive, then the total number of cars in the chain divided by cars per second, right? So that's exactly what's going on here. So this is an example where there's only one car on the highway at once. I send the message, takes a little bit, the entire car has to arrive, and then only when the highway's free do I send another message. So that's what I'm illustrating here. Okay. So the effective bandwidth, the number of bits per second that I'm sending, is N bits divided by the total latency of sending the full message. So that's the 1 over latency effect. So now we can go to a little bit more complicated model. So imagine I'm going to send, and there's a couple of hops on the link. So there's a bunch of little pieces of highway now. So I have the cost of maybe calling the message send API call, like copying the buffer to the network. I have the cost of transferring over the first hop in the network. I have the cost of transferring over the second hop of the network. And all of these steps in the process add to the latency of the system. So if you imagine that the first link has really low bandwidth, which means it takes a long time to send a message over that link, and the second link has really high bandwidth, you can kind of break the time spent sending this message down into a number of parts. There's like the time that the core, the processor, has to spend dealing with the message, like copying it to a network buffer or implementing the send API call. There's the amount of time that I spend in the longest link, which is link 1 here. Not the longest, like the slowest link. And then there's kind of everything else. So the total latency is the concatenation of all 4 of those, or all 3 of those things, and there's like 4 steps in this process here. So does this diagram sort of make sense? Everybody's following this diagram? So if I'm doing asynchronous sends, I can begin to pipeline all these messages, right? So let's imagine I want to send a bunch of messages, and I want to do them asynchronously. So I can, as the orange box is the box where of what the processor is doing. It's working on sending message 1. As soon as it's done sending message 1, it starts sending message 2, and so on and so on. And the network just does its thing on every step of the process to send those messages. So you see how the messages are now being overlapped. While the processor is working on the next message, the previous message is now starting to go out over the wire, and so on and so on. So you can think about every row here as being a different car. And you can think about every sort of block in a row as that message or that car going over a different part of the highway. Except now, like, the different parts of the highway take different amounts of time, which is a little bit more like the washer-dryer example. Are we good? Okay. So if you look at this diagram, you'll notice something interesting happens. Notice that after the processor has done copying the first message to the network and immediately starts working on copying the second message. But when it gets done with the second message, the network hasn't finished sending that first message over the first link. So what do you think we have to do in that situation? So one thing I could do is I could stop as the processor and not do anything and just wait until the network was free. But that's not what this diagram is showing.
Buffer your messages.
Yeah, like I could put those messages in a queue for the network, which says, look, here, I'm copying it to a buffer that you need to know about. I'll stick it away in a queue, and I'll forget about it, and I'll assume, network, that you'll pull it out of that queue at some point later. So the little numbers here on this diagram would be the size of the queue every time the processor puts another message in the queue. And you'll notice that, so right here, after 2 messages, the processor's dealt with 2 messages, the size of the queue is 1. When the processor finishes its third message, the item in the queue has already gone out. If you notice, we start the blue box just before the third message gets finished by the processor. But the processor here can put messages in this buffer faster than the network can pull them out, because the orange box is not as wide as the blue box. So you'll notice the processor is completely busy all the way until here, because this corresponds to that buffer filling up. There's nowhere for me to put the next message for the network and move on to something else. So what do you observe about the throughput of the system? Is the throughput of the system, what part of the system is it determined by? Maybe. So if let's say we made the buffer twice as big, would we be okay? Would the processor always be able to run at full rate? I like the thinking there, but so I like the idea that we're better off if we make this buffer bigger. But I'm not sure if we'll always be running at full rate. So let me go here, yeah. You're always going to be limited by the slowest component in the system, because we're thinking about like throughput over continuous number of messages. So if we take Isha's suggestion and make the buffer bigger, things are good because we'll be able to run longer before the processor has to stop working and wait. But if we think about this out to infinity, for any finite buffer size, we're going to fill up at some point. Okay? So if we're thinking in terms of throughput, it's the slowest link in the system. It's the weakest link in the chain that determines what your overall throughput is. And to go back to the highway analogy, that would be like saying if there was a region of the highway between San Francisco and Pittsburgh where you had to drive 15 miles per hour, that would dictate the whole throughput of the whole system, right? Because everything would get blocked behind that. Or equivalently, the dryer is the system, the part of the system that determines the throughput in doing your laundry. Okay, good. So what we've been talking about is various ways to think about the cost of communication operations in a system, right? And the cost you can think about as like sort of overhead that's spent, like what do I do to get a message ready to go? The occupancy, what's the slowest link in the system, followed by like any other delays. And I can reduce some of these costs by pipelining or overlapping a bunch of these operations. Okay, I gave you 2 examples of overlap so far: asynchronous message sends, pipelining in an instruction pipeline. And when I say communication, even though I started this lecture saying, okay, let's think about 2 computers in the cluster, they're connected via Ethernet, they send messages, I want you to really think about communication as any time you want to move bits in a system. So I think about communication as being, okay, it could be processor to its L1 cache. It could be communication between the L1 and the L2. It could be communication with main memory. It could be communication with some other processor's main memory or something like that. So do not think about communication just as like sending information from here to Google or from here to another machine in the cluster. There's communication within a machine as well, and everything that we're talking about in terms of pipelining and overlapping things can apply to communication at any scale. Okay, so I want to kind of talk about two different classes of communication, but before I go on, are there any, how are we doing so far? Everybody's has done laundry before, and everybody has driven a vehicle, so I believe the analogies are reasonable to comprehend. So I do want to differentiate two different types of communication that occur in any computer program. The first one is I'm going to call inherent communication. Inherent communication is communication that you cannot avoid if you're trying to get the right answer. So for example, in our grid solver, it was absolutely fundamental that processor 1 had to send data to processor 2 in order for us to make progress in the program. There is no way that we could have avoided that send given this assignment of work to the processors. So that's why the term is inherent communication. It's inherent to the algorithm. It's inherent to how we've assigned work to the processors. And if we want to talk about sort of how much communication a program is doing, you'll often hear this metric, communication to computation ratio, which is the amount of communication that you're doing versus the amount of computation that you're doing. I like to think about the inverse of that, 1 over communication to computation ratio, which you'll often hear called arithmetic intensity. I like the term arithmetic intensity because higher is better, and it sounds cooler. Both of those reasons are good enough in my book. So I usually think about, let's increase the arithmetic intensity of a program, because we want most of our work to be computation and less of our work to be communication. Because remember, if we start overlapping the two, we're going to be bound only by the slowest of the two, which is doing work. And as long as we're bound by doing work, we're doing okay. So we want high arithmetic intensity. So let's think about the arithmetic intensity of this grid solver example. So every processor, if this is like say it's an n squared by n squared grid, and I have p processors, every step in this process, how much computation is done by a processor? Is it order, what is it roughly? If you had to quantify how much computation every processor does, and there are n squared grid cells, how much computation does every processor do? P processors, n squared grid cells divided equally. N squared over p. Everybody see that? And so every time I do n squared over p work, I then need to communicate some rows to my friends. I need to lean forward and say hi. And how much communication is there in every step of the process?
2n sends, 2n receive for each processor.
Yeah, I mean, if we're just talking sends, for example, it's 2n. Or if you want to count sends and receives, I'd rather just count sends because that's data is going over the wire once. It's 2n, right? So the arithmetic intensity is n squared over p over 2n, which is approximately n over p, if I just start dropping constants. Make sense? That's just the ratio of those two values. Now let's think about what happens if I went with an interleaved assignment, where I gave every processor, or I interleave the rows onto the processors. So what is the amount of compute that I do every step of the process? What is it? Still n squared over p. I'm still dividing n squared pieces of work amongst p processors. How much compute do I do? Sorry, how much communication do I do? Sorry? 2n squared, or per processor. Per processor. Sorry? Yeah, I mean, every processor, I'm going to communicate that row, every row I work on to every person. So for every element I compute, I'm going to send it twice. So the ratio of elements computed over elements communicated is 1/2. So which would you prefer? you'd almost certainly prefer the one on the left, assuming that n was significantly greater than p. Exactly. Can anybody do any better? So I like this. This is a nice decomposition. As long as n squared, as long as n is much, much bigger than p, you know, I've got a pretty high arithmetic intensity, and I'm pretty happy about myself.
Can we just do everything on one processor?
Well, you could. Yeah, you could. And that would actually maximize the arithmetic intensity. That is correct. But it would hurt what? It would hurt my ability to execute in parallel. Good, okay. So we reasoned through that one. Nice. But is there a better assignment? For this thought experiment, yeah. And if you're not, well, so if you're suggesting, like you're suggesting, that maybe for some application, communication is so high that you're better off just serializing everything and not communicating, that certainly is something that occurs, and it sometimes occurs often. But for this program, you know, we can do better. We can definitely do better. So here, you can think about it in this visualization as the amount of work that we're doing corresponds to the area of every one of these regions, right? And the amount of communication that I'm doing sort of is proportional to the perimeter of that region, right? So if I want to maximize arithmetic intensity, I would like the maximal area to perimeter ratio, right? So you could actually break things up and divide the work to processors this way. And so now the amount of work computed per processor is still n squared over p, right? The elements communicated per processor is 4 times the length of an edge, and the length of an edge is n divided by root p, because there's p processors and there's root p in any one dimension. And the arithmetic intensity now is not n over p, but it's n over root p, which is potentially better at high processor counts for sure. So this would be, you know, this is a very common way that I would split up a big, large 2D grid onto a bunch of processors to maximize the arithmetic intensity of the program. So if inherent communication is communication that we absolutely must do, there's another type of communication called artifactual communication, which is communication that happens because of how the underlying computer works. And what I mean by that is it might be something like, well, maybe you wanted to send one element. Like in this particular example, I only wanted to send one element here to this guy in this row, for example. And maybe the machine requires me to always send 16 or something like that. So artifactual communication is communication that just happens when you think about how your program is mapped to a modern computer. And just a few examples might be, every time you load a value from memory, you get a full cache line, right? So even if you only wanted one element of the cache line, the inherent communication might have been, I needed to communicate 4 bytes from memory, but I actually just transferred 64, for example, on an Intel cache line. And there are other examples, like in network communication, where there's minimum sizes and things like that. So this is a good time to see, and Professor Bryant is in the room, to see what we know from 418. Because I just gave you an example of how the cache is really affecting how much communication is going on. Because let's say I wanted to read one value from memory. I'm like, that's not that big of a deal. You know, it's only 4 bytes. And boom, I just got hit with 64 bytes of data transfer. 16 times more data just got communicated than I wanted to. So in class, in 213, you almost certainly talked about a few different types of reasons why you might miss the cache. Can anybody tell me what a cold miss was? And then they classified them into these 3 types of misses. So what was a cold miss? The first time you access data, you kind of can't get around having to load it into the cache at some point. Good. What is a capacity miss? Go somewhere else in the room. A capacity miss. 213 is a prereq. Everybody in this classroom has had this and had an exam on this. Someone? Yes, sir. the cache line cannot store any more blocks? Or I think I understand what you're saying. You're saying the cache can't hold enough data? But that's actually what we're talking about down here. You're close. But what's a capacity miss? And the key word is capacity. If the cache doesn't have enough capacity, what is that situation? What's going on? Yeah.
You're accessing 5 contiguous integers.
Yep.
The cache can only store 4. So on the fifth one, you obviously have a miss.
Right. So a capacity miss is a miss when your working set is larger than all the data the cache can hold. And you just gave me a reasonable example. Imagine your cache could hold 4 numbers, and your program iterated for I equals 0 to 5 over and over and over again. If that cache had an LRU policy, by the time you got back to element 0, it would no longer be in the cache. That's a cache that's not big enough. It doesn't matter how I organize the cache in any way, shape, or form, I'm going to take some misses. So that's a capacity miss. How do we reduce the number of capacity misses? What's the easiest way to reduce the number of the capacity misses?
Maybe instead of a LRU, you just drop something randomly?
Well, I mean, for the workload I just stated, yes, that might work. But just in general, if I don't have enough space, I can make a bigger cache. Exactly. I can make a bigger cache and reduce my capacity misses. And now, what was a conflict miss? We can go back to. Right. So what is a direct map cache? Here's an example. A direct map cache means what? That every line, every address, every cache line goes somewhere, it can only go in one spot in that cache, right? Direct map. So what happens if I have a cache that can, let's say, it's a megabyte cache, but the only 2 pieces of data that my application is going to access happen to map to the same spot in the cache. And I go load A, load B, load A, load B, load A, load B in a direct map cache. What's going to happen? So first of all, I have plenty of capacity. I have a megabyte of cache. I'm only loading 2 values.
It's going to crash.
Exactly, but I'm going to take a miss on every single operation because whenever I load A, it kicks out B. Whenever I load B, it kicks out A. And so this is a conflict miss because they're conflicting where they go in the cache. How can I reduce conflict misses? Sorry? I could do it myself. I could reorder my code so that, but what if my algorithm fundamentally needed A and B and then A and then B and then A and then B? I mean, I can't imagine. It may not be possible for me to go A, B, 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 B. But if you're an architect, how would you improve your cache so that we don't take these cache misses? What if you made the cache twice as big? That wouldn't help. Yeah?
Randomize like padding.
I could change the program again to randomize, right, to make sure that the 2 values that I need don't map to the same cache line. Yes? Yeah. Sorry? I can move to an associative cache that allows lines to be placed in different parts of the cache, right? Exactly. So I can increase the associativity of the cache. I could change the access patterns in my application, which somebody gave me. Good. Okay. So, and then I want to actually add a 4th C in this class, which is a communication miss, which is a cache miss that you take because the value is off somewhere else in the machine. Like it's been loaded into the cache by another processor, and now I need that value as well. So there's going to be a 4th type of miss here. And those misses could be due to real communication. Like, for example, processor 1 just loaded the data and updated a red cell. And then processor 2 needed that red cell to compute its black cells later. The data is kind of in cache, but it's in the wrong cache. And so we have these communication misses. So has anybody seen a figure that looks like this before? where the x-axis is the size of the cache, the capacity. The y-axis is the amount of traffic to main memory, or another way to think about it is kind of the number of misses that you take, cache misses that you take. And so as I increase the cache, notice that the size, notice that the number of cold misses, the number of misses that are cold misses don't really change. And we talked a little bit about any kind of inherent communication can't go away because I have to communicate those values. But you notice that the number of misses is dropping as the capacity increases. So does this make sense, first of all? Does the diagram make sense? Has anybody seen a diagram like this? Okay. One person seen a diagram like this before? Two people? So imagine you were an architect at Intel, and you got this, you ran a measurement on your program, and you could run this architectural simulator. You could increase the cache size, because you're trying to figure out, you know what size cache should we build in our new processor? And the only thing your job was to do was run this program really well. It's the only thing the processors. What cache size would you choose? What? You could choose this cache size because it would maybe give the great performance, but it could have really high cost because you're building this really big cache. So you just used up the entire chip worth of transistors to build some big cache. So are there certain points in the design space that this diagram might indicate are good places to potentially choose? You sure you're nodding your head?
The point before the third slant. I mean, yeah, that point.
Right here?
No, go down.
Oh, right here.
Yeah, that one.
Okay, and what about right here? No. What about right here?
Maybe.
Okay, so what is, let's compare, I could choose that cliff or this cliff. I'm going to choose this one because I'm standing here. Would you choose a point right here, or would you choose a point right here? The right side. And why is it smarter to choose a point on the right side? But what does that mean? There's a steep cliff. I agree, it's correct. Usually it's good to stand at the bottom of a cliff than rather right on the top. That's good life skills. Yes, sir.
If you go left, that means there's a big penalty for you. But if you go right, there isn't much.
So if I'm sitting right here with this design, with just a little bit more cost, a little bit more effort, I could have gotten a huge performance benefit. Or if I'm standing right here, as Isha was thinking, I might as well have just built this tiny little cache because it was just as good. Exactly, right? So, and by the way, does the graph on the previous slide look familiar? It better. Because you've seen it before. And only 2 people in the class said I've ever seen a diagram like that, just for the. Okay, so let's talk about reducing communication a little bit. So imagine that this is our grid solver. Same thing. We have this array. We've kind of assumed that it's laid out linearly in memory. And we've kind of assumed I've always written the for loop of for all I, for all j, and so on and so on. And imagine your cache line is 4 grid elements. Imagine your capacity is 24 grid elements, so 6 lines. So the blue data here are all the cache lines needed to compute that red dot. And so remember, because you only take the sum of your neighbors. So if I want to compute the red dot, I need those cache lines. And if I go in row major order, I get to the end of the grid. And these are the cache lines that are in memory when I get to the end red dot. Those are the last 6 cache lines I've touched. And assume everything is LRU. When I get back to the next row, something bad has happened. None of the data is in cache because, well, those are the lines that are in cache, but some of the elements that I could have used to compute the red dot used to be in cache. So first of all, what type of miss is this? Capacity? Conflict? Some people think conflict. Some people think capacity. Why do you say it's capacity?
Because the thing is, if you have a bigger capacity,
Yep.
in this case, you'll be able to cover the whole.
Yeah, I mean, the cache is full at this point. So had I not loaded those lines into the cache, I would have taken misses over there. So my working set here is a row, and I'm going to need, or 3 rows, and 3 rows cannot fit in cache. So does anybody have a solution on how I can improve the arithmetic intensity of this program, the number of operations per unit cache miss, in this case, without doing anything really hard. Yeah?
If you can't increase your cache easily, you could,
Yeah, I can't, like, I'm giving you the computer, right? You're not going to ask for a bigger cache.
so you could start at the end of the row and go.
Yeah, actually, you could. You could actually come back in this direction. Yeah, that's actually an interesting idea. But that only gets you some reuse for just a little bit. And imagine that this is like n equals 1,000,000. Does that make sense? So your solution, like I get to the end, and I come back around, and I get some good reuse. But then as soon as I keep going back, now I'm back in the same boat. So so that's a step in the right direction. Absolutely. Anybody else? Yeah.
You could kind of like do like one part of the row at a time, then go to the next row, and as the other one is being loaded in, you kind of do the next row, and you do that like row kind of.
Right, you could take a blocked iteration order to maximize your reuse. I drew this here just to make it very clear. Ignore this as like an edge case, and imagine this n is really big, and you can imagine going across 3 cache lines all the way down like this, and then going back up to the next thing. And if you actually do the math, and I don't want to do the math in front of all of you right now, just because I'm worried about time, is this particular operation, where was it? If you noticed, the original code loaded 3 lines for every 4 elements. So every time you process 4 elements, you actually were bringing in 3 new cache lines. This restructuring moved me up to 3 lines for every 8 elements. So I've kind of doubled my arithmetic intensity, and if this happened to be a bandwidth-bound operation, I just improved the performance of my program by a factor of 2. Because remember, I'm limited by how much data I transfer. That's the longest, that's the blue box. That's the longest part of the pipeline. And I just cut that down by a factor of 2. Let me give you another example, which is really, really big these days. So has anybody used NumArray in Python? They're like, okay, really, really fast, right? Because you call add this vector onto this vector, and it's implemented in C code. It can even be parallelized. You can be like, add these vectors, now add these vectors, multiply these vectors. Has anybody used MATLAB? Exactly. Okay. So what I'm drawing here at the top of the screen is imagine like you had some math library that gave you like large vector add, mul, add, or something like that. And you wanted to use my math library to do E equals big vector D plus A plus B times C, or whatever. I just made that up. And what you would write in MATLAB would look something like this, right? Add the A and B, multiply A and B times C, and then add C to D. Is exactly how we think about this mathematically in terms of vectors, right? Very, very clean, very, very nice. Now notice that every single one of these operations does 3 loads for every math op. The arithmetic intensity is 1/3. And almost certainly will be completely bandwidth bound on any modern machine. If I was to write this code, I might take this whole sequence of math operations and reorder the whole computation, so that for every element in the array, I'm just going to go ahead and do A sub I plus B times C plus D and write the output. And notice in this code, I load 4 values. I load A, B, C, D, and I write E. And I have 3 math operations for every 4 loads. So I'm about 1 math op per load. Here, I'm 1 math op per 3 loads. My arithmetic intensity just increased by a factor of 3. This program is almost certainly bandwidth bound on any machine you'll ever run on. This code is 3 times faster. And of course, if you have a long sequence of operations, add, mul, divide, whatever, like you have a long sequence of NumArray stuff, you're just by fusing them together, just by reordering this computation, which is another example of an optimization like this. You know, if I have a sequence of 25 operations, I just made my code 25 times faster. And that's why you'll see some of these programming systems that automatically do fusion for you like this just blow away anything like MATLAB or any of these systems that just say, okay, if you give me a big array, I'll do that, and then I'll do the next thing, and then I'll do the next thing, because they're going out to memory every single time. Right? Okay, so we talked about reordering data. I don't want to talk about too much, but you can also share data amongst your threads. And that's exactly why CUDA shared memory is there, right? Instead of every thread loading all the data it needs, the threads cooperatively load all the data that they will share and only do that once. And then they access that data over and over again out of that shared memory, right? So that's another little little detail. Okay, so I'm going to skip this. Another example, actually, so we were just really happy with ourselves when we went to blocking the grid in the squares, in the tiles, to increase the arithmetic intensity of our program. We were really happy with ourselves. But then imagine if the data is laid out in row major order, even though this processor only needs one element here, it might have to load the data at the granularity of a cache line. So even though the inherent communication is one column, you might get, in this case, 4 columns, or in a real processor, you might get 16 columns worth of data. So even though we just asymptotically improve the communication to computation ratio, we have artifactual communication under the hood if you're not thinking about how the cache behaves. Even worse, and I'm going to talk about this later in class, imagine if you completely divided your array into 2 chunks. Every processor worked on a different chunk, and the way you divided it happened to straddle a cache line boundary. So that whenever thread 0 and thread 1 are writing to these cache lines, even though they're writing to completely different elements, they're actually writing to the same cache line. So as we'll talk about shortly in this course, there's some severe performance implications of this, because that cache line is actually moving back and forth to service processor 1, and then going back over to processor 2, and so on and so on and so on. And if you looked at your code, you're like, there's no sharing at all. So things can be very, very, very tricky. Okay, so I want to conclude in the last 5 minutes with the last part of this process. And the last thing that's going to bite you is imagine that you go to office hours. Heaven forbid you go to office hours, right? And imagine that students, and in fact, this is one of the reasons why up until this year I never had scheduled office hours. I was like, make it by appointment only. So imagine that 2 students make an appointment with me to have office hours, and somebody says, I would like to talk to you at 3, and somebody else says, I would like to talk to you at 4:30. And students are hanging out in the Gates Cafe. So it takes about 5 minutes to walk. Well, it doesn't really take 5 minutes, but let's say you stop and talk to a friend. It takes 5 minutes to walk from the Gates Cafe to my office. So the entire operation of going to office hours is, well, you walk 5 minutes. You get your question answered. Maybe it takes 5 minutes. And the whole latency of the operation is 10 minutes. 10 minutes, you've got your brilliant answer from your friendly professors, and you're on your way. And then the student 2 does this at 4 p.m. They walk 5 minutes to my office. They get their question answered in 5 minutes. The total latency of the operation is 10 minutes. Okay. So now imagine, the time cost to the student. The cost to you is 10 minutes. Now imagine I just have office hours, 3 to 4 p.m. And what's going to happen if most people are going to try and show up right at the beginning of office hours. So I have all these students showing up, let's say roughly kind of right around the beginning of office hours. They all leave the Gates Cafe, they drop their lattes, and start walking over. And now remember, it takes me 5 minutes to answer a question. And this was happening at office hours last night. And so the first person shows up, they get to me at 3 p.m., they're out of there, 3:05, 10 minutes of their time. The second person also shows up at 3 p.m., but I'm busy talking to somebody else. So they have to wait, that's the gray bar, until 3:05. And they get their question done. They're done by 3:10. So it took them 15 minutes to deal with office hours. And like other students that come right after those students end up waiting for 20, 25 minutes because like this student, so the time cost to the first student, 10 minutes. Time cost to like the third or fourth student that arrives, 23 minutes. Which suggests what about when you should show up for office hours? You should either show up as early as possible, but then you have to hedge and all your weight comes here because I can't service your request until 3 p.m. Or everybody should coordinate and do what? Like spread out their arrival times over the entire office hours. Because as long as, in the 1 hour, I can do 12 students, right? I only have 60 minutes, so I can get 12 students through the pipeline. And as long as they kind of space themselves out, they're only going to spend 10 minutes of their time. So this is an example of contention. Contention happens when you get bursts. When a bunch of people where a bunch of threads want a shared resource, such as a bunch of threads want to update a shared variable, like in the reduce example. A bunch of threads want to take a lock, and they all want to do it right at the same time. One example from the previous lecture is we moved from a shared queue to a more sophisticated system where instead of all the worker threads contending for the shared queue, all the worker threads had their own queue. So we duplicated the queues to eliminate contention on the shared queue. Another example that happens in CUDA programming all the time, actually, is contention for memory, which is kind of interesting. And remember, you just created this thread block with tons and tons of threads to hide latency. But they kind of all run in lockstep. So if I do load from the input in memory into local data, all the threads do it at the same time. All of them issue their memory requests. They don't come back for 100, 200, 300 cycles. And all of those threads are sitting there at the barrier waiting for their memory request to come back. So even though I just had 128 threads, or maybe thousands of threads to hide latency, all of them are actually doing a memory request at the same time. So I didn't really do anything useful when they were all working, right? And so that's why an interesting rule of thumb actually is to make sure that you have a couple of thread blocks on a machine at once, because all the threads in a thread block are probably going to access memory or barrier or be blocked at the same time. It's kind of useful to have another thread block to be able for that core to do. So people have been asking me, can CUDA programs run multiple thread blocks on a core? And the answer is absolutely yes, and in fact, it's highly encouraged. So this lecture, I have a bunch of other fun examples, but I would like to close with this example. So let's do this for a few minutes, because we got started just a few minutes today. So imagine you had a problem, which was I have 1 million particles, billions of particles. And I happen to have a really parallel machine, let's say the Titan X supercomputer, or maybe, for example, an NVIDIA GPU, where there are lots and lots of processing cores, lots and lots of threads that can run on the machine at the same time. And imagine I wanted to build a data structure where I wanted to build a grid, a list, or I want to build a data structure which contained a list of all the IDs of all the particles that happen to fall in each of these grid cells. And these are point particles. And the reason why I like to build these data structures is, for example, in an n-body computation, you might want to know for any any particle here that's red, what are the particles that are within some radius r of that particle? And if I have a list of all the particles in every grid cell, I could just look in the grid cells around the red particle and really quickly grab only the particles that are probably within radius r. I wouldn't have to look over all the possible particles. So building a grid where there's a list of particles in all of the, a grid where there's like an array and I have a list of all the elements in a particular grid cell, is a pretty useful thing to do in many, many scientific computing applications. So if we wanted to do this, perhaps the first thing that I would do is I would parallelize over the cells. For each cell C, for each particle, if the particle is within the cell, add the particle to my list. Perfectly parallelizable, right? What's the problem here? Sorry? Oh, I didn't say that in order. There's no need for order. I don't care. I just want to know what lists. I want all the particles in a list. Everybody's free to go, by the way. I mean, it's 4:21. You guys should go. Question? Oh, so for each cell in parallel, sequentially just add the particle to the cell. Well, there's no n, but so one problem is that I actually am testing particles against cells like p times c times. So I'm actually doing every particle against every cell 16 times, and I only have 16-way parallelism because I'm only parallelizing across the cells. So if I go 16x parallel and do 16 times more work, kind of not a particularly interesting solution, right? So of course we could parallelize over the particles. I have billions of particles. I have tons of cores. I could parallelize over those particles. And for every particle, I could compute the cell containing P. But then if I wanted to put that particle in the right list, I have to take a lock on that list. Because all these different threads are like writing into the same particle, or into the same cell. Well, that's kind of rough. So then I could say, well, no, let's reduce the contention on that lock by let's make a lock per cell. So now I have 16 different locks, and so I have 16 times less contention, right? On average, like it's much less likely for people to be contending for the same lock. Any other solutions? Does anybody else have any other ideas? Yeah.
Have a set of 16 lists per like worker thread and merge them.
That's a very reasonable answer. You could say, you know what? I'm just going to compute the problem completely independently on a bunch of threads, and I'm going to make 16 or however many as many as I want, independent grids of lists, and I can always put them back together at the end. That's an interesting solution. And then interestingly, I can also do one that's strikingly similar to your quiz assignment tonight on how you might be able to do it if I just gave you a sort and a data parallel map. So I'll let you guys take a look at this offline, and we're good, I think, for lecture now. Yep. Okay.